the chapter that was on small signal stability analysis, and then we had some little bit of discussion about the oscillations which we observe. In this part of the discussion, our focus will be on what is oscillations, and then uh, how we perform the study related to the oscillations. So as this part, what I mean to say, what should be the model, or what is the typical model that we use for the study of electromechanical oscillations. I will consider a simple example of a network or a model uh, in respect to the study on power oscillations here. And on this slide, as you can see, uh, because normally when we have a power system of wherein you have the generators, and you will have several generators, right? And some of smaller size, some of larger size in terms of the capacity, I mean. And then again, some generator will be driven by hydro turbine, and thus you may have silent ship generators. And then some generators will be driven by steam turbine, right? Or maybe it could be either the coal-based power plant, or maybe the nuclear power plants, and thus they have cylindrical shape generators. So you have wide range of generator size and the types here, which are interconnected by the network, and the impedance of the network
Sir, your
will
voice is audible.
okay, okay, but I have it here, if I can see. Now can you check?
Yes, please.
Sir, it is audible. It was also.
Sir,
I'm audible now?
Yes.
might be
Earlier also.
Yes, please. Can you confirm?
You are audible, sir.
Yes, sir, you are.
Okay, fine. So then again, I think I have to start the recording. Or it is stop. Okay, fine. I will do that. So as I said, we have wide range of generators, and some of them being of hydro generators, and others being at steam turbine driven generators, and then again of different capacity. And these are being interconnected by the different impedance of the line network. And then you have several types of the load as well. You may have static load, or composite load, or the dynamic load. So, but we want these generators to operate in a synchronized way, uh, and again at a desired frequency, right? So can you confirm if I'm audible now? Clear?
Yes,
Before
sir,
I
you are audible.
Yes, sir. Now.
yes.
Fine, thank you. So if in case speed of one of the generator deviates from the synchronous speed, then it will indicate that imbalance. There is an imbalance between the power available from the generator side and the power demand from the load side. And thus the deviation in the frequency will actually express or reflect the power change in the system. And when this takes place, then it will be important to maintain the synchronous speed back, because whenever there is a disturbance, frequency will deviate out from the synchronous speed, and then it will be your objective to get back to the synchronous speed, or within the range that we require. And to get back to the synchronous speed, uh, that will be achieved by some action, and that is by some controller action. You have to change the gains of the controllers. It could be on exciter side, right, or it could be on turbine side as well. So you have to apply some way of control actions on generator so as to get back the frequency uh, to the nominal value or to the desired value, I mean. Yeah. However, low frequency oscillations that may adjust if the setting of the controllers or the state of the network is inadequate. In fact, even now, it has not been clear indication saying that it is because of this reason we have the observation or we have the occurrence of low frequency oscillation. It is very difficult to say it is because of this reason low frequency oscillation exists. It is very difficult to say because the system is very complex, and there is no definite reason saying that it is because of this low frequency oscillations takes place. So but uh, we can say that such oscillations, low frequency oscillations, they may take place, they may exist whenever you have some disturbance, and following the disturbance you change the setting, because you will change the governor, you will change the settings of the governor controllers basically, right? And that may the gains, I mean, this change in the controller action or maybe the system network itself, that may result into low frequency oscillations for the change in the operating condition, right? In particular, we have high speed excitation systems, which is for preventing against the loss of synchronizing torque and thus to improve the transient stability. Uh, in fact, the excitation system, maybe I will discuss later on in the slides. We have the use of excitation system, and these excite because we are talking about the low frequency oscillations, and these are actually the electromechanical oscillations which are associated with the rotor angle, right? So because these oscillations, they are associated, and thus with the use of high speed excitation systems, it is possible to prevent the weakening of the synchronizing torque. That means reduction of synchronizing torque, that is possible, and thereby improve the transient stability. So in one way we have the use of high speed to improve the transient stability, right? uh, but these excitation systems which are used to improve the transient stability in other way, all right, in other way, tends to weaken the damping characteristics of low frequency oscillations. These excited systems, though they improve the transient stability because uh, they prevent the reduction of the synchronizing torque, but they weak because we have the damping torque and this synchronizing torque actually, right? And thus these excited systems, they can reduce the damping torque and thus the damping characteristics and resulting into the low frequency oscillations, because low frequency oscillations, they are related to the damping torque here. So they may try to reduce the damping torque and thereby result into the low frequency oscillations. So this is, again, it will depend upon what is the operating conditions, and then what is the gain setting of these excitation systems basically. Uh, Now with this slide, as illustrated, I think we have also discussed earlier that how we are likely to have the oscillations, and you can see here uh, we have a graphical representation. And then when we talk about the phasor position, so when we say the phasor position, it means that the variation of rotor angle for one generator and the variation of rotor angle for another generator, they are exactly 180-degree phase shift here. And thus the, as I said, you can use the angle state variable or the angular speed here, but as reflected we have the angular speed here. So thus the vector representation for angular speed for the two generators when they are in phase opposition, they will be 180-degree phase shift here. Then we also have the generators oscillating in the same phase, and in that case we observe that the oscillations of one generator and then again some more generators here. Thus the all the generators, they will be oscillating in the same swing. All right, because this is one swing, this is one swing here, one cycle of swing, and all the generators, they follow the same swing here. But one of the generator will be oscillating dominantly because you can see here that its amplitude of oscillation is much more. However, other two generators, their amplitude is little bit lesser. And thus in the phasor representation, as you can see that one the generator which with a higher amplitude, this is the phasor length. And for other generators, it could be comparatively lose uh, lesser magnitude of phasor length here. So thus, as in this case, this generator will participate dominantly because it is oscillating with a higher amplitude here with respect to the other two generators here. Though they are in the same phase, but the amplitude of oscillations may differ here. Okay. So this is phase opposition, and here it is the in phase oscillations. I have not shift, but you can say you can imagine what could be the oscillations when there is a phase shift by 170-degree, 120-degree, and so on here. So next, this slides tells you how we have the classification of the power oscillations, and we have referred some literatures which are available. In fact, power oscillations, they can be as natural one because of some natural behavior, you can say, or it is due to some controller gain setting or the operating point change and so on, you can say, or the network property, you can say. So this is natural. Another could be as a unnatural, and here it could be some cyclic nature of some disturbance, and thus because this is related to some cyclic nature of disturbance from the load side, and that's why it is referred as unnatural word here. Now then in the natural oscillations, power oscillations, they could be as inter-area mode or local mode here. I will discuss more in detail about these modes later on. However, and these modes, they can be well damped or they can be with a low damping factor, weakly damped. Similarly, local mode, they can be good, they may have good damping factor or they may have poor damping factor. Unnatural ones, they can be at limit cycles or the four oscillations. And again, these form of oscillations, they can be of sustained nature. So they will exist for few cycles of swing occurrence here. Now, maybe this classification of power oscillation, you will not observe in detail in any of the book. In the Kundur book, it is not given here, but you may get in a few papers actually, that is possible. Because this form of the unnatural oscillations we have in the power system. We have observed in the power systems in the last 1 decade actually. We didn't had any information about this form of the oscillations taking place in the power system earlier. And that's why it is we don't have any control action against these form of oscillations. As of now, we don't have. But for these types of oscillations, local mode and the interior mode, we have the plan available now. Right. So I move to the next one, and here this slide tells you or gives you information about what are inter-area oscillations and the local mode. We say about the inter-area oscillations between the two groups of the generators here, which will swing against each other. So as I said, I think in the earlier class that we have an oscillation between the generators located in the south of Finland and the south of Sweden, right? And thus, so those located in south of Finland and Sweden. So these are the two groups of the generators, and they oscillate against each other, right? So this will be as a inter-area oscillation here. So oscillation between two groups of the generators which swing against each other. And in this case, the oscillating frequency could be it is lower, 0.1 hertz to 0.7 hertz, you can say. And here, several generators and the areas involved, they are involved in oscillations. Okay, so you may have several generators, and again, you may have one area or the two area, other areas, that is possible. So you may have several generators and as well as areas being involved in the oscillation. It is possible. However, as I said, the local, because when you say the local, that means the observe in the generators locally. So that means we have the oscillation in a smaller number of generators, but it will be against the rest of the system. So that means we have few sets of the generators oscillating against the rest of the system, against all other generators, I mean. So it is not as an area defined now. So you observe the oscillations in a dominant way only in few sets of it could be all the generators in one power plant, or it could be one power plant which is located to nearby to another power plant. So you will have generators in power plant 1 which is closely connected to the generators in another power plant. So these generators in the two different power plants which are closely connected, which are closely located, I mean, they may have the oscillation of local mode of type, and they may have oscillations against the rest of the system. And in this case, the oscillating frequency is much higher comparatively. So here you have some or all the generators in the same power plant or the nearby being involved against the rest of the system. So this is how we can categorize or they classify the two different types of electromechanical oscillations. Anything here? No, then I move to the next one. Nothing so far?
So in the when we talk about local area, that means only few generators, and inter area means generators of area 1, all the generators in area 1 with respect to the generators in area 2. Correct?
Yes. Yeah.
So inter area only involves two generators, or could be more because you have
It could be
different.
more generators. but it will be several generators in area 1 and another several generators in area.
Okay.
That is to say, the group of generators in area 1, this will be these groups of the generator in area 1, they will be of coherent nature. Then another group of the generators in area 2, they will also be of coherent nature, and they will be oscillating against each other. So, but remember one thing, it is always against each other.
Okay, sir.
Okay. But local mode will be, it will remain within the generators itself. You will not observe these oscillations in the tie line. Okay, you will not observe the oscillation uh, in the power flow uh, that adjusts between the power plant and the rest of the system. But these oscillations, inter-area oscillations, you will observe even in the tie line. That means the line, transmission line that connects the areas. You will observe the oscillation in that tie line. But local mode of oscillations, you will not observe in the tie line. It will adjust locally in the power plant, you can say. Okay, that means
Okay.
if you get the signal, delta signal, because rotor angle, you can translate it to the voltage angle actually, right? The bus angle. So if you observe the bus angle in the substation, then in that case, you will observe that there is some oscillations here. So, but it will not be observed in the tie line. Okay.
Yes, sir.
So next we move on to the topic because we have the analysis of the power oscillations with the models, and the most simplest model that we use for the study for the analysis of power oscillations is the single machine finite bus system. So here that means we have a system, we have a generator with the prime mover, and this is the bus generator terminal, you can say, which is connected through a line to a large network. So you want to understand how does this generator will oscillate against the rest of the system here. So we want to understand the oscillating property of this generator against the rest of the system. So, and the most simplest model that we have, it is the single machine finite bus system, or it could be referred as Heffron-Phillips model here. And as you can see that we have a generator with the prime mover, and then it also includes the governor here. Now, in some cases we have the governor included, in some cases we don't have it, because normally the oscillations they are somehow related to the state variable from excitation system, and thus in most of the modeling approach for the SMIB, they have actually excluded the governor, but in the figure shown I have just included the governor also, because on the prime mover we have the governor included, so I have just for the representation purpose I have included the governor, but in the modeling part, the equations for the governor I have not included. It is just for the representation only here, not for the modeling aspects. And then you can see here that you have the field winding for the generator, and then excitation systems, and then AVR part, and as well as you can see that we have the feedback of omega signal to stabilizer, and then this stabilizer they feed signal to the AVR section at the reference summation point. Yeah. So in the modeling part for the generator, we have the use of full order of generator equations, but we have some simplification. saying that the effect of the winding damper windings they are neglected. Then the effect of fast transient and the resistance of the D and the Q axis windings, they are neglected because we want to analyze the low frequency oscillations, and thus which are actually slower, comparatively, and thus we don't want to include the dynamics related to the transient effect. So we don't have it here. Then, hello beta, please. Then, because as I said, we want to have small signal oscillations, so we are concerned with the variation of rotor speed here, and we say that variation of the rotor speed is very small because we want to analyze the small signal stability here. Hey, beta, beta, I'm studying, beta. Beta, you go away from here. ले जाओ. Just later. Better you go and study another room. Go. Bindi, I'm studying. You look here. You go away from here, please. Okay, bye bye. Okay, sorry. This slide tells you uh, how I think okay how we develop the model for SMIB system, and what is the purpose? Because we want the simple representation for the machine for stability analysis. This is the objective, and we use the third order model of synchronous machine, and from the swing equation, as you can see. So this is the linearized swing equation, and in terms of omega and small deviation in omega and small change in rotor angle here, and these two equations they are represented in the block diagram here. So you can see 1 by 2 hs plus kd. So this is the damping constant, damping factor, and then system inertia, and then the rotor angle delta. So if you have the integral of omega, the delta here, and then the difference, because will be the change in the power or the torque here. So that's this is the mechanical torque, and this is the electromagnetic torque, the difference of the two, and that is the you can say the delta change in the power here, which will result into the accelerating power here, in the swing equation. So this is actually the accelerating torque or the accelerating power here. And then we move to the next one. We include the electrical torque part, and as I said that if you refer from the previous discussion, in the SMIB representation, we have several constant, but I will not go into detail on the derivation of the constant, but time being, you can understand that this electromagnetic torque is represented in terms of some constants here, and V1 is the K1 times delta here. Another one is the K2 times the del EQ prime. So this is the generator internal voltage here, right? And that is del EQ prime here. So, and thus we have the generator state variable del EQ prime, and thus this is one state variable, and then these are the two state variables. So thus we have third order model of a synchronous machine in these in these three state variable form, right? And then we include the effect of voltage regulation, that will be through the field winding part, that is excitation systems here. So to include the effect of the field circuit, we have another constant here, K4, and then the field circuit representation here. This is one. Then we move another one. So we want to model the terminal voltage. So we have now excitation system, and then here we have the dial EF, so that is the field voltage terms here, and this is your reference voltage set point here. So normally voltage reference set point delta change, it is kept 0 because reference voltage is the desired value. So we do not change it actually. So delta V reference, it is normally 0 here. Then you can see here that we have some more terms in terms of K5, and then because that will be del UT or del ET here, and then del K6 times del EQ prime. So del ET will be equal to K5 times del delta plus K6 del EQ prime here. That is del ET. I have not included the voltage transducer at this part, but in some block representation, you also have the voltage transducer part here included. Now it is possible to, as I saw here, you can see that the excitation system is represented by first order system here. All right, you have just the amplifier gain and then the time constant of excitation system. So just by first order representation, you have an excitation system. But in some cases, you can also have the IEEE type 1 excitation system. And if you remember, this is what we have discussed in the type 1 excitation system model. You have amplifier part and then intermediate state variable here. All right, because this is S term here, so there will be some intermediate state variable, and then exciter part here. And then again, if you remember, this was the stabilizing transformer representation, so another state variable here. So you can have more detailed representation for the excitation model, and thus instead of using a simple system as here, you can have few more terms being added, right? So and thus if you want to write down what will be the state variable, so you have it dial EFD, one state variable, then you have one state variable, another state variable here out of this, and then you have the third state variable out of this here. So thus you can write down 3 state variable for the excitation system here, right? And here this could be the signal that you have from the transducer part here, this one. Then again another signal you can get it from the power system stabilizer part here. So this is all the summation point here for the AVR section, right? And next, as I said, we want to include the PSS exciter here. So this one, this is the complete excitation systems. As you can see here, this is dial EFD and V reference. So this is the complete, you can say, the representation for excitation systems. It could be the detailed one, or it could be the simplest one here, as indicated here. Or then with this exciter represented, with the, let's say this is some transfer function. So you may have the signal from transducer, as I said. So you have the signal from transducer. So this is dial VT. And then you may have the signal from stabilizer at AVR part. So this is your reference voltage summation. So this is the stabilizing signal from the stabilizer. And then you have the power system stabilizer blocks. So you have a signal dial omega, because let's say you want to stabilize the oscillation you observe in the dial omega signal state variable, right? So you have some gain, you have some low pass filter, you can say, or washout filter, and then some compensating device here. So you have some lead lag compensator here in the PSS blocks. And if you want to write down the state variable out of here and this state variable out of here, then you can note down these 2 state variables here, right? I think I have not written VS here. What I have it here, dial V1 here, it is this one. in terms of this, and then again you dial VW in terms of this here actually, right? And then as I said, this PSS, instead of having this conventional PSS design, you can also have the PID implementation. So if you want to have PID implementation, so thus uh, the the compensation part, that means VW, between VW and VS, this compensation part you can by the three gains of PID here. So you have input VW and dial VS. So thus we have the compensation being replaced by PID structure. And as such, you may have few more state variables here. So X3 and then dial VS in this form. So you have it here. And then you get the complete block diagram representation for SMIB. So as I said, this is your inertia model. Then you have the field circuit, dial prime, and then this could be your exciter. It could be simple exciter or the detail model. And then you have the voltage transducer part and then your PSS part here. So that could be the complete SMIB system for the analysis here. And that's then it could be the PID base. So here I have added two more terms and then you may have PID. And then as I said that like this exciter you can have replaced by detail one. So you have this exciter, the IEEE type 1 excitation system referred here. This is one part. And then the PID structure being referred in here, right? So for this case, now you observe that because here we have mechanical torque and the electromagnetic torque. Now, if you want to include the turbine and the governor section, then this state variable will be from the turbine part, and in the feedback it will be the governor in the turbine section. So that can also be included. But we, as I said, we will not model the equations for the turbine and the governor. So we will just consider some disturbance in the turbine mechanical power here. That's all. So the difference between the mechanical torque and the electromagnetic torque, that is as a input. And we have the rotor angle delta, as you can see here, that will be as an output variable here. So this difference will be the input here. Then now that means you can apply a step change here. Let's say you want to observe the state variable. How does the rotor angle changes? So this is your output variable, right? So you can apply a step change, some 1% or 2% or 3% change in the turbine mechanical power. Then you have another input here. So you can have some disturbance in the reference voltage as well. So thus you can observe the dynamic behavior of the rotor angle variation either with this disturbance or you observe with this disturbance here. Okay. So this is one part. Then again, the electrical part of the system, because this is more or less like you can say the mechanical representation, mechanical section part of the SMIB. Then other part which we have it, this is the electrical part section here. So in the electrical part, you have the electrical torque, which is influenced by del delta over the K1 constant and the del Q prime over the K2 constant. If you refer here, this is del TE. So this is the electromagnetic torque, K1 times del delta and K2 times del Q prime. So this is first term. Then we have the effect of field winding, which is determined by the constant k3, and it is influenced by delta over constant k4. So if you go back, so this is your del eq prime. So in fact this one, so you have k4 times del EFT, and then this field circuit part here. So this is second part. As I said, the field winding constant k3 and k4. Then you have an excitation systems influenced by del delta with constant k5 and del eq prime with constant k6. So if you refer here, you have k5 del delta, k6 del eq prime. This is del vt, and then with the transducer, it will all go to excitation system here. So this excited systems will have the signal out of through the transducer with this one, actually del Vt. So which is actually K6 times del eq prime and K5 times del delta here. In this case, the excited systems, as I said, it is modeled by IEEE type 1, but it can also be represented by simple transfer function with the constant gain and the time constant here, excitation. And thus you now it will be your work to obtain the complete state variable which we have, and you can see that there will be these are the state variables through which we have modeled the SMIB, and there are two input variables and you can say two output variables. So you can say del omega and your del delta, that could be as your output variable that you can define here. And then I said, yeah, here I have listed down the complete equations here. So that, so you have all these state two variables. This omega naught you can consider your reference, so it could be your as a value as for 50 hertz it is 314 radian per second, and for 60 hertz it will be 377 radian per second. So it is this one, right? So maybe